Hey everybody, glad you could join here for the help session. Listen, I first want to go over what you expect for exam, what is this, exam 3, and this is 1 week from Wednesday, or in about a week, it's next Wednesday. It's going to be on Moodle. It'll be monitored by Responda, so you'll need a webcam, you'll need all that set up. If you're uncertain about how that works, make sure you go online and there's a trial quiz. You can just try it out. There are unlimited attempts, I think, that you can make on that. Or if not, ask me, I can set it up for you. But make sure that everything's functioning properly. I did an exam this morning and everything went just fine. But I don't want any hiccups, any technical hiccups. That exam 3 will cover the end of chapter 4. I'll call it chapter 4B. And in that, we have multi-loop circuits. We have RC circuits. And household circuits. So you'll need all of those, multi-loop, RC, and household circuits. In chapter 5, we'll have all of chapter 5. That's going to include the right-hand rule. There are 3 cases of the right-hand rule with the curl rule and then the QVB and the ILB using the right-hand rule to find the magnetic field or the force, the current. Let's see, you're going to have mass spectrometers. How that works, you'll have defining the magnetic field due to a long straight wire. The magnetic field due to 2 parallel wires. Let's see, solenoids. Hopefully I'm getting all these. It's going to be all of the chapter, so I'm just trying to remember what all the different topics are. Finding the force, that's the F equal QVB sine theta. And then also F equals ILB sine theta. This mass spec, by the way, that was using this equation, R equals MV over QB. I think that's right. I think that's all for chapter 5. And then chapter 6, we've already covered chapter 5 in a help session, and likewise chapter 4. Next week, if we have more questions about these, then we'll address those. But tonight, I just want to address chapter 6. And chapter 6 is a fairly short chapter. It's just on reflection and refraction. And I'll go over each of those, but in short, light, when it reflects, this angle is equal to this angle. Theta I is equal to theta R. That's reflection. Of course, some of your problems are a little more complicated than that. And then refraction, a couple of things. First of all, when I go from one medium into another, the speed of that wave can change. If the index of refraction is different, the speed will change. And then if I go at a certain angle, where this would be the angle, theta 1, it can bend depending on how the index of refraction is different. And I had a question from one student. I think it was the only question that I had for this help session. It's just, how do you determine if the ray bends towards the normal or away from the normal? And that student, who by the way is an amazing student, sent me this image of a problem from a screenshot where I asked, what is the direction that a wave traveling from air to glass bends? So imagine I have air, glass, and I have a beam of light traveling from air to glass. Now, I know that for air, the index of refraction is equal to 1. And the index of refraction for glass is bigger than that. It turns out to be, I think, 1.5. By the way, if I wanted to know the speed of light in glass, I would say V is equal to C divided by N. That's 3 times 10 to the 8th meters per second divided by 1.5. No units on the index of refraction, by the way. It's a ratio of 2 velocities. And so that's going to be 2 times 10 to the 8th meters per second. So the light slows down quite a lot when it goes into this new medium. the way that we figure out, I always have to think about this. I like to draw a band of wave fronts. And there's an analogy, I talk about this in the notes, there's an analogy that relates it to a marching band. Maybe it's just because I was a band geek in high school that I like this analogy, but I think it works well. That a band is supposed to move all as one. And so when one side of the band slows down, then that sort of messes up the band. So what happens here is when this band of wavefronts, this wavefront of light, enters into the medium, this part right here slows down. So I have slow on this side, but this side is still fast because it's still in the air and it just travels, 50% faster in air. 3 times 10 to the 8th versus 2 times 10 to the 8th meters per second. So what's going to happen is this whole thing is just going to turn in this direction, which is going to give me a ray of light that will bend towards the normal. So if I'm moving from low to high in, I bend towards the normal. If I move from high to low in, I bend away from the normal. Okay? By the way, the normal is this line. It is a line that is perpendicular to the surface of the material, and the angle that I measure is always the angle from the normal. I rarely measure this angle. In optics, I almost always measure from the perpendicular line. Okay, let's look at some questions from old exams. Here I'm looking at, what is this, the spring 18 exam. And by the way, it would be very important for you to practice the old exams in these upcoming next couple of exams. I know that you do that, but I want to make sure that you're doing that everybody is practicing the exams. You have every exam that I've ever given for Physics 102, and I really need you to know how to work all of those problems. There's probably a few hundred for you to practice. So, a few hundred? 100, 200 maybe. So, I want you to really be practicing those. Usually these are exam 3, but you might find some questions in exam 2 or exam 4, so we have to find the right topics. Let's see, these are all right-hand rule stuff. Okay, number 20. This is a great one that's related to what we were just doing. Light travels through 3 media as shown here. Which medium has the highest index of refraction? So, I'm going to draw my wavefronts. It's going to slow down there, and then that's going to move over. That's why it's bending towards the normal. So I know that medium 2, light travels slower. Because light travels slower, N2 has to be bigger than N1. Okay, so medium 2 has an index of refraction that's bigger than medium 3. So I can get rid of that right away. And now, when I'm coming here, this ray of light is going to speed up and go in that direction, and that's why it bends away from the normal. So light travels faster in medium 3 than it does in medium 2. That means that N3 is less than N2. I'm looking for the one with the highest index of refraction. So if N3 is less than N2, that means that's not an option either, so it has to be B. Now note that if instead this ray of light followed this path, oh, geez, I didn't know I could do that. Since it follows that path, all right, so I have to pause this, my pen's messed up. If it were to follow this path right here, where it's bending towards the normal, the angle's kind of, that would mean that it is slowing down when it enters into medium 3, and if it looked like that, then I would say N3 is bigger than N2, and in that case, it wouldn't be B, it would be C would be the answer. But for this problem, the answer is B. So the ray bends depending upon how the indices of refraction are different. Don't try to memorize those little rules. I always like to use the marching band analogy. This are these wave fronts, and I ask myself, okay, Is it slowing down or is it speeding up? If it's slowing down, that means that the index of refraction has increased. If it's speeding up, that means that the index of refraction has increased. See, one of you also asked about this question, or something similar, and you're very likely you will have a problem like this related to reflection. The thing about reflection is that the reflected angle, which is this angle, is always equal to the incident angle, which is that angle. So in this case, this angle is 60 degrees. And also, this angle right here is a 90-degree angle. So if the reflected angle is 60 degrees, then that means that this angle is 30 degrees. Now, I have a right triangle right here. And since this is 30 degrees, this is 60 degrees. And if that's 60 degrees, then this must be 30 degrees, and that means that the reflected angle is 30 degrees. So on this problem, which is an application of the law of reflection, then the reflected angle off the second mirror is going to be 30 degrees. That's another problem that you'll have. You'll also have some problems that are just about the electromagnetic spectrum. I'll give you a problem something similar to this where you have to list them in order of lowest energy to highest energy. You'll see lots of different problems that are similar to this. Of these four, infrared is the lowest energy. That means I can get rid of that one, and that one. And then it goes infrared, visible, X-ray, gamma ray. So B is going to be the right answer. So know them in order of increasing energy. Also know them in order of increasing wavelength and frequency. Now frequency is simple because energy is proportional to frequency. And so if I ask you for the order of lowest energy to highest energy, it would be the same for frequency because they're proportional to one another. But if I asked you for wavelength, energy is inversely proportional to the wavelength. So for example, radio waves, which have a really small energy, have a very large wavelength. So if I'm keep that in mind as you're ranking your electromagnetic spectrum for either frequency, energy, or wavelength. I want you to know a little bit about the history of light and why the different scientists have thought that light was an energy or a particle. You'll absolutely have one or two questions about that, probably just one. So Newton, that's what you need to know. Newton thought it was a particle because of reflection. And he was reasonable in thinking that. He just didn't have the whole picture in mind. Huygens thought light was a wave because of refraction. And likewise, he was reasonable. Newton and Huygens lived in the same time period. In fact, they battled over these ideas. Fast forward 100 years or so, Young, no relation, I don't think, thought it was a wave based on interference. Very good reason to think that it was a wave, and that held for 100 years until Einstein, who came about, and he already knew that this happened, but he postulated that light was a particle because of the photoelectric effect. So you need to know these four people, these four particle or wave, what they believed, and then why they believed it. So for example, this is wrong because it says interference. This one's wrong because it says photoelectric effect. That's not why he thought it was a particle. Huygens believed light was a wave, but not because of reflection. And Newton believed light was a particle, but not because of refraction. So look, none of these are true is the answer here. You'll have some questions like this, where I ask you just what is the refracted angle. And to do this, use the law of refraction, n1 sine theta 1 equals n2 sine theta 2. This is on your equation sheet. n1 is the first index, that's glass. The index of refraction for glass is 1.5, and the incident angle is 30 degrees. And n2 is for air. The index of refraction for air is 1. You're expected to know that the index of refraction for air is 1. It's the same as a vacuum. Equals to sine theta 2. And then I need to solve that for theta 2. Now, you will be allowed to use your regular calculator. People did not like the calculator that we have in the quiz, so you will be allowed to use it. It's a terrible calculator. All right, so this is 0.75 equals sine of theta 2. And so the inverse sine of 0.75 is 49 degrees. Okay? You'll have some question about the speed of light. I showed you that earlier, but it could be something like this one. When light enters into a medium, its speed slows down, and that speed is equal to c divided by n, which is 3 times 10 to the 8th meters per second, divided by the index of refraction, which here is 1.5. So the speed of light in this fiber optic cable is 2 times 10 to the 8th meters per second. Now, if I want to know the time in nanoseconds for it to travel this distance, I would say v is equal to x divided by t. That's not on your equation sheet, but it's an equation that you should just sort of really know. It's one of the fundamental kinematics equations, that speed is distance over time. So if I'm solving for t, that's x divided by v, which is x is 0.6 divided by 2 times 10 to the 8th meters per second. That's going to be 0.3 times 10 to the minus 8 seconds, or 3 nanoseconds. So that would be your right answer there, and I would expect a question like that. Okay, goodness, did we have... Yeah, I think we did have total internal reflection. So you will have a total internal reflection question as well on this for this chapter. And the total internal reflection is really just a special case for the law of refraction. The total internal reflection, or the law of refraction, is n1 sine theta 1 equals n2 sine theta 2. In total internal reflection, the refracted angle is 90 degrees, so this is equal to 1. It's really just a special case for our refraction. And so n1 sine theta 1 is equal to n2 times 1. Let me show you what I mean. Say I'm going from glass to air. There is an angle wherein the light ray will not enter into the air, where there is an angle theta 1 such that it bends so far away from the normal that it doesn't bend here, that it bends so far away that it has a refracted angle that is equal to 90 degrees. So this theta 2 would be equal to 90 degrees. Let me show you here that if I have a situation where I'm going not from glass to air, but from air to glass. Think about, does this light ray bend towards or away from the normal? If I have a light ray that comes in here going from air to glass, does it bend towards or away from the normal? Now in the previous scenario, it bent away from the normal. But think about here, my wave front comes along, it slows down here, that means it speeds up. So this guy is going to bend towards the normal. That means I can never get any total internal reflection in this scenario moving from a low index to a high index, just because the light ray is bending the wrong direction. It's bending towards the normal instead of away from the normal. So for total internal reflection to occur, I have to move from high index to low index. And if you have a question about that, just think about a fiber optic cable. A fiber optic cable is a thin sheath of glass, a cylinder of glass, and the light ray travels in it, and it never escapes. It's just surrounded by air. Now, fiber optic cables often will have some sort of cladding around them, but it's really just to keep the glass from getting damaged. It's not to keep the light inside of it. So it's because I have a high index surrounded by a low index of refraction material. Now, the angle at which theta is equal to 90 degrees is called the critical angle. And I think in this one, well, we'll get back to number 23. But I might ask you, what is the critical angle? And so let's just do that here. I know this is 1.5 is n. This is n equal 1, and so I would say 1.5 sine of theta is equal to 1 sine of 90. And then I'd solve that for theta, and I would find that theta is the inverse sine of 1 divided by 1.5, so that's what, the inverse sine of 2/3, or 0.67, is 42 degrees. So that would be my angle. Let's look at number 23. So the core is in the middle of the fiber. The cladding covers the core and protects it. You have two media, flint glass and crown glass. Which of these will serve as the cladding? You wouldn't actually use crown glass for the cladding, but the one that you want to use for the cladding is the lower index of refraction. Okay, so it'd be B would be the right answer. The lower index of refraction material always goes on the outside of our fiber optic cable for a total internal reflection. Let's see, that is the next. Okay, so that's sort of the end. Our chapter 6 ended right here. Let's look now at the other exam. I have the spring 19 exam here too. Let's just sort of take a look. Make sure you're good on all these electromagnetic, electric circuits, magnetic fields. We can look at that in our next help session. Let's look at, well, let's think of this. Which of these following statements is true? X-rays have a longer wavelength than ultraviolet radiation. Well, let's think. I have radio waves, microwaves, infrared, visible, UV, what comes after that? X-rays, and then gamma rays. This is increasing energy in this direction, and also don't forget it's also increasing frequency, and our wavelength is increasing in this direction. Radio waves have an immense wavelength. They're centimeters or millimeters, but they can also be kilometers or hundreds of thousands of kilometers, the wavelength for some radio waves. So X-rays have a longer wavelength than ultraviolet radiation? No, they have a shorter wavelength. Huygens believed light was a wave because of interference. He believed light was a wave, but only because of refraction. In fact, they didn't really know about interference in his day. Light has a dual nature and can behave either as a wave or a particle. Aha! So Newton had incontrovertible evidence that light was a particle because of the photoelectric effect. Behaved absolutely like a particle. But Young had excellent evidence that light behaved as a wave. So, in quantum mechanics, we have this idea that there is this dual nature of light, this duality of light, where light can behave as a particle in some cases, and it behaves as a wave in other cases. So number 3 is correct. And prisms separate white light into its colors because the prisms are triangular. Not because they're triangular, but because of the index of refraction, because of n. So only 3 is correct. Oh, let's see, let's do this one. These two mirrors sit at an angle of 130 to one another. A ray of light is 60 degrees first. What is the angle of reflection? Once you do these a bit, they become easier. If this angle is 60, that means that angle is 60. That means this has to be 30. 30 plus 130 is 160. This is a triangle, so this has to be 20 degrees because a triangle has a total of 180 degrees. And 30 plus 130 is 160. 180 minus 160 is 20. That means this angle has to give, it's our complementary angle is 70 degrees. That means that this angle is also 70 degrees. Which of these statements is true? Does light travel faster or slower? Well, if it's traveling along here, it's going to slow down, so this will speed around, so light travels faster in medium 1. Here's some speed of light ones. Here's a critical angle. Remember, that's n1 sine theta c. is equal to N2 sine of 90. That is how we define the critical angle. But if I'm moving from a liquid to a gas, that is from 1.75 to 1.52, okay, that's okay. I'm moving from a high index to a low index. And so that's good. I can have total internal reflection, so it's not B, I know. I would say, what's my 1.75 sine of theta C is equal to 1.52. I'm not sure what the critical angle is, but you can calculate that. Okay. I think we'll stop there. I know that's kind of a short help session. Is that short? Yeah, but we move a lot faster when there aren't students in the room, unfortunately. So you can pause and slow down. If you have additional questions, let me know. We'll do another formal help session on Tuesday around midday next week, so you send me your questions. But hey, listen, I'm here. I don't really do anything all day. Actually, that's not true. I'm really quite busy these days, but I'm never too busy to meet with you virtually. We can do a Zoom session or a Google Hangout. I have a little whiteboard here at my house, and we can meet and talk about the particular problems that you're having. I would love to do that. So if you need some special help, you're all special, and all of you need special help at some point. But if you need some personal help, then I'm here to help you, okay? So just send me an email, give me a call, or we'll video chat. Have a great day. Bye.